Told you about this last time. Keep in mind, material for which you are responsible on any quiz or exam depends on where we are in class. Never mind what the syllabus says. If you're with us in class, you know where we are. And if you're not with us in class, then it doesn't make any difference. If I tell you where we are, it still won't make any difference. Because if you're not with us in class, you can't possibly know what we're doing. Now, we are in position at long last to start to get at the real meat and potatoes of acid-base chemistry. What happens reaction-wise in an acid-base system when a reaction occurs? You cannot possibly understand the chemistry of a system unless you know what's in the system. That's why we have labored to bring to your attention the idea of inventory. Because by writing a correct principal species inventory for each system that we study. What are the possible systems? Pure substance, solution. That's it. By writing correct principal species inventories for these systems, we at least start by knowing what we are dealing with. Then we have a chance to understand the chemistry of the resulting system is created when we start with these individual systems and mix them up. Now, the rules of the road for writing an equation for a reaction. Because the simplest way to express what happens in a chemical system, specifically a reaction, is to write the correct equation or equations for the reaction or reactions which occur when the system in question is prepared. And if you've made the principal species inventories correctly, then you can play this game and win. And without the principal species inventory, you have no chance to do this correctly. It's impossible. So to facilitate the foundation, or understanding the foundation for this, the principal species inventory stuff, I made this slide, which we talked about at least in part last time, which some of you talked about completely in discussion class. So what do we got here? System, pure substance, inventory, the substance itself. Water solutions, the second possible system. Well, it is. In any water solution, the main ingredient will always be water itself. So that's always going to be part of the principal species inventory. Principal species inventory. What else is in the system? The only way you can know what else is in the system is to understand the chemistry which occurs when the system is prepared. Like when we make hydrochloric acid solution. We have recognized that HCl molecules react with water in, say, for instance, preparing 1 molar HCl. To an extent which, practically speaking, is 100%. It is 100% for 1 molar HCl. Upshot, principal species inventory for 1 molar HCl solution is water solvent, hydronium ions, chloride ions. That's it. HClAQ, forget that stupidity. It's not there. Something that isn't there can't react. I don't see any reason why I should have to explain that. But the textbook authors, I have to explain that. They don't understand this yet. Well, forget that. All right? So really, that's the hard part. What is the chemistry that occurs when you make the solution? Well, we've provided you with the rules of the road for writing these principal species inventories, so that in essence you will know the chemistry that occurs when the solution in question is prepared. Because the species which result come from that chemistry, come from that reaction. So here we go. Ionic compound. Ionic compounds always dissociate when they dissolve in water. That's a chemical reaction, a decomposition reaction. If you know the formulas for the ions of which the compound is composed, then at least you know that dissolving the compound puts those ions in solution. In most cases for ionic compounds, that will be the principal species inventory. But sometimes these ions, like metal ions with appreciable positive charge densities, +2, +3, rather than +1, will form well-defined hydrates, like Al+3, which forms hexaaquo-Al +3, like iron +3, which forms hexaaquo-iron +3. Do you see these formulas in the acid-base table? You bet you do. All right. Next, strong acid. Oh, one of the batteries died. Can you hear me all right? I have a big mouth. That's usually not a problem. All right. Strong acid. 100 milliliters of 1 molar HCl, for which in this case I've written a QPSI. Remember what that means? Q means quantitative. And in chemistry that means how many moles. So for 100 milliliters of 1 molar HCl, we will have in that solution 0.1 moles hydronium ion, 0.1 moles chloride ion, and about how much water?
55.5-ish.
If we had 1 liter, we'd have about 55 moles of water. We got 1/10 of a liter. So we got about 5 moles of water. 5.5 moles of water. Good enough? Wonderful. I didn't write that there. That caught my eye when I was mentioning the fact that I had a QPSI up there for the HCl solution. Weak acid. What's the primary difference between the chemistry of a weak acid versus the chemistry of a strong acid when water solutions of each are prepared?
A weak acid responds to much less than 100%.
A weak acid will react with water to make hydronium ion. That's why it's an acid, because it reacts to make hydronium ion. But the extent is small. Now we're going to find out that for certain weak acids, by progressive dilution, by making the solution very dilute, making the concentration very small, we can get weak acids to ionize to an extent that exceeds 50%. We'll talk about that finer point later, not now. We'll now work with the simple rule of the road that for a water solution of a weak acid, and this statement applies to any fairly concentrated solution of the weak acid, like 1/10 molar or greater. The main solute species will always be the weak acid itself. And if the weak acid is provided to the system by a salt like ammonium chloride or sodium hydrogen sulfate or aluminum chloride, then beside the weak acid itself, you'll also have the counter ion. Because you've got to recognize ammonium chloride, sodium hydrogen sulfate, aluminum chloride, these are ionic materials. Okay? Strong base. Leveling effect, like with the strong acid. Now we're going to get the hydroxide ion at high concentration, well, at the same concentration as the dissolved base, and the conjugate acid of the dissolved base. All right? Now, Let's see if I can adjust this so we can see the rest of this thing. There we go.
I have a question for aluminum nitrate. The ionization or the dissociation of it. Why isn't it 0.3 moles of NO3?
Right there?
Yeah.
It is 0.3 moles. But I, like a dummy, didn't pay attention to this. So I'll fix that. See that error right there? Let's fix it right now. $10 points for you, minus 10 points for me. Can you read what I wrote? And let's see. Now we're not going to bother with the quantitative mole count for the water molecules. We talked about that. Good. I told you. Sometimes my nose gets too close to what I do and I mess up. Don't let me get away with that. If you think I mess up, you holler. All right? Potassium oxide. Oxide, the strongest base listed in our acid-base table. At the very bottom of the base column. Given that bases get stronger in our acid-base table from top to bottom, which they must, because the stronger is an acid, the weaker is its conjugate base, vice versa. So if the strongest acids are at the top of the acid list, the weakest bases in our table will be the conjugate bases of these strong acids. And they're at the top of the table. The bases are getting stronger from top to bottom because as we go top to bottom in the acid column, the acids are getting weaker. And when we get to oxide ion, which is the conjugate base of the acid hydroxide ion. How good of an acid do you think hydroxide ion is? Not much. Base, yes. Acid, no. We're looking at the strongest base in our acid-base table. Upshot, when you put any source of oxide ion in water solution, the oxide ion reacts with water to create hydroxide ion to an extent of 100%. So per mole of oxide ion dissolved, you wind up with 2 moles of hydroxide ion. The oxide ion that collected H plus from the water molecule, and the hydroxide ion which results from stripping H plus from the water molecule. And all oxides are salts. So the counter ion will also be present. In this case, it's potassium ion. Right there. Potassium sulfide, an ionic compound. But sulfide is a strong base, stronger than hydroxide ion. So when we dissolve K2S, dissociation puts K plus in solution and initially sulfide ion in solution. But the sulfide ion reacts immediately with water to make hydroxide ion and hydrogen sulfide ion reaction extent of 100%. That's a proton transfer reaction. I don't know when you talked about kinetics in 2045 if you talked about rate of proton transfer reaction in solution. Anybody talk about that? Nanoseconds. That sound pretty fast? Nanoseconds? 10 to the 9th seconds? Reaction rates for these H plus transfers? You think there's much hindrance to H plus swimming around in water solution? Do you know that if you got a whole string of water molecules and H plus hits this water molecule on this side of the string, then immediately on the other side of the string H plus pops off? Just like that. It is a description of H plus transfer mechanism. What happens to it? I left it off. That's terrible. 10 points off for me, 20 points off this time. Can you read that added scribble? 0.2 moles HS minus AQ. Good. I don't know how I did that. That's stupid. Me. All right? And then the last thing is weak Bronsted base. Like weak Bronsted acids, bases react with water, but to a limited extent. In most cases, quite small. And if the initial molarity of the weak base is on the order of 10th mole or greater, the extent will always be small. Consequence, we can inventory correctly for principal species in a water solution of a weak base, the weak base itself, and counterions if the source of the weak base is a salt, like sodium acetate. Okay? Now, let's get at the task of writing equations for reactions. To do that, we've talked about this, so I'm going to cut this off so it's not in our way. Lynn, pull the shade over the shutter. And now with better illumination we proceed. Here's the rules to write these correct equations for acid-base reactions. Number one, write PSIs for each acid or base or solution thereof that you're going to deal with. Number two, you examine these PSIs. And with the support of the acid-base table, you can immediately at a glance recognize if the acid in question is a strong acid or a weak acid. If the base in question is a strong base or a weak base. Acid column. The strong acids are hydronium ion and every acid above hydronium ion. In our table there's only 4. Perchloric acid, sulfuric acid, hydrochloric acid, nitric acid. The rest of the acids down to and including water are weak acids under hydronium ion. The acids under water, hydroxide ion and HS minus, are weaker bases than water, weaker acids than water itself. Upshot, practically speaking, these things never get in the acid behavior game in water solution. Water's a stronger acid, and water outnumbers them significantly, to say the least. Bases, only 3 strong bases listed on our table. What are they? Hydroxide, sulfide, oxide. That's it. Then as we move up the base column, above hydroxide ion and until we get to and including water, we see the weak bases. The bases in the base column above water are again the bases which are conjugates of the strong acids, which means they are weaker bases than water. Which means that practically speaking in water solution they don't get a chance to behave as bases. They will not affect pH in water solution. They just swim around merrily and be what the textbooks refer to as a spectator, like you watching the Gators. So, with this information, you can, after you write your PSIs, or pardon me, you can, in order to write the PSIs, recognize, are you dealing with a strong acid, a weak acid, a strong base, a weak base? And as far as pure substances are concerned, pure substance is itself. That's how it inventories. So now, step 2, you look at your PSIs, and with the support of the acid-base table, you pick out the strongest acid, and you pick out the strongest base. Because if any H plus transfer is going to occur in a system, it certainly is going to involve the strongest acid present in high concentration or amount with the strongest base present in high concentration or amount, and that will follow immediately from the PSIs that you've written. So you write the reaction equation, and the last step is, does this equation which you wrote represent a reaction which goes large extent or small extent? How do I decide? I look at the reaction equation. I look at the reacting acid and the product acid, and I compare their strengths. If the reacting acid is a stronger acid than the product acid, I've made significant progress toward increase in stability when I go from stronger to weaker. That extent is large, and vice versa. If I go from a weaker acid to a stronger acid, the extent is small. Does that not keep with inventories for water solutions of weak acids? When acetic acid reacts with water, I make hydronium ion and acetate ion. But hydronium ion is a much stronger acid than acetic acid, isn't it? That's why that reaction only goes to a small extent. But if you write that reaction in the opposite direction, now you're looking at a reaction that goes to a large extent. And why is this important? As we have reminded ourselves, the simplest and best way to describe a chemical change in a chemical system is to write the correct or best equation that we can for that chemical change. Here we go. Question 1810. Hydrogen chloride gas, the pure stuff, is mixed with nitric acid solution. Every time you see this M label, you know you're talking about a water solution, because this M means molar concentration. And we're not dealing with any solvent other than water. So there's the inventory for that. What's the inventory for this? There it is. Nitric acid. Strong acid. So when we make 1 molar nitric acid solution, the nitric acid molecules react with water to an extent which is, practically speaking, 100%, and in so doing gives us a solution containing hydronium ion and nitrate ion. And of course, water solvent. Since water is the solvent, water is the principal component of that solution. So now from step 2, look at this inventory. Don't forget this part, that's part of the inventory. What's the strongest acid in this system which I'm about to create? I'm going to put HCl, pure stuff, in that water solution of nitric acid. What's the strongest acid in my inventory? HCl. What's the strongest base in my inventory? Use the acid-base table as necessary. Use it as a crutch. What is the strongest base?
H2O.
It's water. So we write the reaction equation. We know this is the reacting acid, this is the reacting base. This is the acid produced by this reaction, because the reacting base gets converted to that acid by H plus grad. And this is the base produced by this reaction, the conjugate base of the reacting acid. Last step, extent. We already know the extent of this, don't we? But let's look at the rule. Look at the acid column. How does the strength of HCl as an acid compare to that of hydronium ion? HCl is stronger, isn't it? Now, if you want to play with the bases, you'll always get the same result. How does water as a base compare strength-wise to chloride ion as a base? Water's stronger. Extent, large. Now, we know this one's really 100%. All right? System B. 1 molar HCl. Now we got a solution of HCl. You recognize that this reaction equation we just wrote shows us the solute-derived species for HCl solution? How about that? So for this system, we got hydronium ion, AQ. I'm going to leave that off for expediting matters. Chloride ion, AQ. Ammonia, water. Ammonia, base, strength, weak, PSI, ammonia itself. And ammonia is not an ionic compound, not a salt. So there's no counter ions. All right? Here's our complete inventory, PSIs. Strongest acid? What's the strongest acid here? Hydronium ion. Strongest base? Ammonia. So, we now have hydronium ion getting together with ammonia. To make product acid ammonium ion and product base water. What's the extent? Large or small?
Large.
This acid stronger than this acid, isn't it? Isn't it? This base stronger than this base. So, large. C. Now I've given you a hint that this time, to respond correctly for C, you have to write two equations. You have to write two equations as a consequence of QPSI for C. Question?
Yes, in the acid-base table it says that water is stronger than, or no, wait.
It's a stronger acid.
No, you looked at the wrong column. That's all right. We'll proceed. As we said, oftentimes it is necessary that your inventory must be quantified, the QPSI issue. This shows us why. Sodium hydroxide solution, 1 molar. Na plus AQ, hydroxide ion AQ, water. Sulfuric acid. I wrote the formula for sulfuric acid with my structurally preferred formula. What's the PSI for sulfuric acid solution? Tell me and I'll write it. I'm listening. Absolutely not. Not one H2SO4 molecule findable in that system. None. Notice that in our acid-base table we recognize sulfuric acid to be even stronger acid than HCl, right? So to what extent does H2SO4 react with water when you make a water solution of sulfuric acid? How much? 100%. So where are these H2SO4 molecules? They're all used up. There isn't a single one of them that you can find in this solution. So let's go for this inventory again. What is in this solution? I'm listening. I got hydrogen sulfate ion. What else? Hydronium ion and water. That's it. Now, we've already done enough of this to show you why. You simply cannot rely on the textbook to do this stuff properly. Because they do not pay attention to inventories, they do not pay attention to chemistry, yet they call themselves chemistry techs. Phooey! They're not getting that trash in this classroom. Not as long as blood flows through my veins. Strongest acid. Now this inventory spread out. Here's the sodium hydroxide solution inventory. There's the sulfuric acid solution inventory. Strongest acid. Hydronium ion. Strongest base. Hydroxide ion. In this case, the product acid and the product base are one and the same, both water molecules. Tell me, do you recognize that this reaction equation corresponds to the equilibrium reaction to which we attach the label Kw? Remember the value for Kw? Do you remember the value for Kw? 1.0 times 10 to minus 14. So what's the value for that reaction, K-wise? It's 1 over Kw, isn't it? 1.0 times 10 to the 14th. Does that support the conclusion that this is a large extent reaction?
Yeah.
Do you know what the magnitude is of 1.0 times 10 to the 14th? That's 100 trillion. That means when this reaction runs, for each one of these, there's 100 trillion of these things. For each one of these, there's 100 trillion of those things. Does that sound like large extent? You're damn right. Now, we've reminded you. To deal with C correctly, you must consider the QPSI. Because what we have done so far by this reaction is to eliminate from the system, practically speaking, which original system component? Have we killed all the hydronium ion? Have we killed all the hydroxide ion? What have we killed? You see what this 2 milliliters, 1 milliliters, do you see these molarities are the same? Okay? When I made this solution, for every liter I put in a mole of sodium hydroxide. And when I made this solution, for every liter I put in a mole of sulfuric acid. But I'm using twice as much as this solution. That means I'm using twice as much hydroxide ion, and twice as much sodium ion. But who gives a damn? The sodium ion doesn't do anything chemistry-wise in this system. It's the spectator. It's the thing that bought the ticket. And not surprising, because sodium ion is damned unreactive, unlike the atom from which it is derived. That's sodium. Is sodium unreactive? We'll talk more about that later. And so, I am forced in this case, after having written this reaction equation, to pay attention to the fact that I'm now looking at a system which at present is imagined to contain both hydroxide ion and hydrogen sulfate ion at high molarity. Because no chemistry as yet has involved hydrogen sulfate ion. And how much of the hydroxide ion did we use up so far? Half of it. So we go back to our acid-base table and recognize from the PSI as it stands at this point, we got hydroxide ion with hydrogen sulfate ion and the presence of water. Are hydroxide ion and hydrogen sulfate ion happy with each other? Are they compatible species? Do you know what the word compatible means? Do they get along peacefully, happily, lovingly? Hydroxide ion and hydrogen sulfate ion? Or do they murder each other? So we got to write another reaction equation. Proton giver, proton taker. Product acid, product base. Extent? Large or small? This acid compares how to this acid strength-wise? Do you see that hydrogen sulfate ion has shown itself in our table to be the strongest weak acid in the table? Sounds like double talk, doesn't it? But it is the strongest weak acid in our table because it is taking the position immediately underneath hydronium ion. Extent? Large. All right? Wait. Water is a stronger base than hydrogen sulfate ion, right?
I thought HOSO3 was a base.
It is a base. Anything with a negative charge is a base. That doesn't mean it's strong. I don't know where you're at regarding what you're not seeing. All we did was to pay attention to our PSI over there. Before we wrote this reaction equation, we realized we have a system which is now containing hydroxide ion, hydrogen sulfate ion, and water. And we asked the question, are hydroxide ion and hydrogen sulfate ion compatible species? And we said absolutely not. Because hydroxide ion is a strong base, and hydrogen sulfate ion is the strongest weak acid in our table. So we follow the rule. Our strongest base now is hydroxide ion, as it was originally. Our strongest acid now is hydrogen sulfate ion. Originally that was hydronium ion, but we killed all that. So we wrote a reaction equation. Acid hydrogen sulfate ion with base hydroxide ion. Products. And then we said, what's the extent? Well, hydrogen sulfate ion is a heck of a lot stronger acid than water, so the extent is large. End of story. All right? We go to E. D. We're going to dilute aluminum nitrate solution. Now, that means we're taking our half-molar aluminum nitrate solution and applying to it what change? Adding water, that's all we're doing. So this question obligates us to recognize what happens to this system, if anything, when we add water. Well, aluminum nitrate solution. What's PSI? Does this look familiar? What's the strongest acid in this list? What is it? Use the table. It's the hydrated aluminum ion, isn't it? I know you're not familiar with this stuff. That's why I keep hollering. Use the table. Use it like a crutch. It's your encyclopedia of acids and bases. And the strongest base? Water. And I trust you remember what considerations you had to make in order to be able to write the formula for the conjugate base of a species like this. You're removing a proton from one of the water molecules that's part of the composition of this stuff. Because this is behaving like a Bronsted acid, isn't it? An H plus giver. So there's our reaction equation. We determine extent. This acid is much weaker than this acid. So the extent is small. And you might say, well, why the heck did this happen? Because I had aluminum ion mixed up with water. The subtle point here is, in this system, as with any system of a weak acid or a weak base, equilibrium exists. Do you remember that? Always equilibrium in any system of a weak acid, weak base. So what you're really asked to consider in diluting is to recognize that when you dilute any water solution of a weak acid or a weak base, you're operating on this equilibrium which involves that weak acid or weak base solute. And at the instant at which you add water, what happens to the equilibrium? It's killed. And the reaction which will take place to reestablish equilibrium is left to right or right to left. Well, we added water, didn't we? And for this to proceed, aluminum ions have to meet up with water molecules, don't they? And when we up the ratio of water molecules to aluminum ions, don't we give a better chance for aluminum ions to hit water molecules and react? Hell yes. So we know for sure by adding water, by diluting, more of this stuff reacts. So the reaction which occurs to get us back to equilibrium is this, which is what we wrote over here. Now, I want you to tackle the remaining parts of this puzzle, and we'll finish that on Monday. But if you really want to make progress with this, you work on this before Monday, or at least before class.